This particular presentation is the second dealing with the maps and images that you can gather off the internet to look at your schoolyard. For the folks that are involved in the Lens Schoolyard project, this follows the presentation that described the different maps and images and what you can get off of them in general. This particular presentation talks about 3 different schoolyards across the state as examples of the kinds of things that you can find out using the stuff off the internet before you go out into the yard. Because the goal of this project is for students to learn more about the nature of science by forming hypotheses, by looking at the information that's available on the internet about what's in the ground and on the schoolyard, and forming testable questions before they go out into the schoolyard. Then the schoolyard investigation can be an exploratory project, but all of that, of course, is based upon what is available on your particular property. The maps and photographs we talked about before are these, and we will show you examples of these at each of the 3 different sites. The first one we're going to take a look at is out in the Valley and Ridge section. Happened to pick the Christiansburg High School simply because we knew that there was going to be a lot of features there that would be examples. You could find examples like this all across the Valley and Ridge from Front Royal down to Abingdon. The blow-up of the geologic map shows that the area is underlain by carbonate rocks, limestone mostly, dolomite. The high school sits on top of a hill, as you can see from the topographic map. If you look at the stream patterns, clearly all the water runs away from the top of the hill. And if you look at the slopes then of the side slopes draining down to those incised stream valleys, you can see there's some flow directly downhill, of course, but it's also largely, again, draining away from the top of the hill. Notice clearly that this area has this is a new construction compared to the age of the topographic map, and that will come to play in what we're going to talk about later as well. So water flow directions is the principal thing you can get from the topographic maps. The aerial photography for the Christiansburg School shows the fields and the buildings, the parking lots. There are not any major drainage lines like ditches or culverts or whatever that can be seen here, but as you could make this map into a base map, just print off a copy and let the students use this as the place where they record information. They may well be able to put arrows and indications of downspouts and ditches and flow directions all across the site. This image also serves as the wetlands map because it turns out when you turn on the wetlands, none of them show up on the school property. Even so, you can still use this area to investigate questions about water flow direction, water quality. You can sample it at various places, particularly coming off the parking lots or off of some eroded areas, and also soil composition questions. What you can't do, of course, is to investigate differences between non-saturated and saturated soils, oxidized and reduced soils. And that turns out sometimes to be some of your most dramatic changes. One thing you can see on the aerial photography here, which is kind of interesting for this site, is that there is a spot that has been eroding apparently for some time because there is a trail of sediment then washing almost all the way across the parking lot. Might be interesting for students to ask how long has this been going on, because the historical photography that you get on Google Earth may let you pinpoint how long this has been happening. The soils map for the Christiansburg High School you see down here in the southern middle portion where we clicked on it. It's describing the soils there for the gross, close, and papillamento soils. These are both clearly reddish, probably well-drained kinds of soils, very typical of what you're going to expect on limestone. If we look at the details of this, we see clearly they are well-drained, and no, they are not wetland soils. And in the parent material, of course, they talk about the various types of rocks that these soils can form on. Limestone, shales, siltstone, sandstone are all, of course, sedimentary rocks. Those aren't necessarily exactly the mix you will find here, but certainly you would expect a lot of weathered sedimentary rocks. Particularly, you will expect, perhaps, if it's limestone residuum, that often ends up being a gray, sticky, red, sticky clay. So let's see what we have down below. In the percent sand, silt, and clay, you see it starts at the surface with maybe about 20% clay, but jumps up to almost 50% clay at depth, which is quite clay rich. In the sand category, it's actually relatively sandy at the surface, but then the sand drops off as the clay picks up. So certainly would expect as you would dig a hole here very quickly, you would get down into some good firm clay. And not unexpectedly, I guess, the KSAT, the saturated permeability, drops off dramatically. It goes down to actually just 3 millimeters per hour. Now remember, to get this permeability, you can dig a hole down to a certain depth, maybe a couple, 3 feet, fill that hole full of water. As soon as the water then drains out the bottom of the hole, then you fill it full of water again, and then you measure how fast it drops. So you want to be looking at the saturated conductivity. And obviously at 3 millimeters per hour, this is going to be a pretty slow draining soil. Now the question is that you can ask here, and most places, is how accurate is this information? When you go and look at a variety of holes across the schoolyard, do you find these numbers? Do you find this percent clay, sand, and maybe this permeability rate at different places across the schoolyard? If not, why not? Another thing you can ask, looking at these maps at this point, is the variation in topography from what is actually mapped there to what you actually find when you go out. I suspect, never having been to Christiansburg High School, that they didn't build the football field over with a gully running down to the middle of it. So I suspect where you see the purple box there, they have filled in that valley to make the flat football field. They may well have taken the dirt to fill in the valley from the top of the hill over where the building was constructed. So I imagine there's been a great deal of construction cut and fill that would certainly affect then the soil composition and soil characteristics as you go select your places to sample. Another site here that would also perhaps have some differences would be the front of the school. You can see on the topography that there is some rather pronounced gullies or small stream valleys that were present there before they built the school. And in those areas on the soil maps, you see actually a number of different types of soils, including this one called Ernst. And if you look to see what the profiles, block diagrams look like for the Ernst, you can see that it shows up as little terraces along small stream valleys. So one of the questions you might ask is, are these valleys and these little terraces still present in the landscape now when you go out and sample? So the overall picture then we have of the Christiansburg High School, where it sits in the general landscape, is that it's going to be sitting on top of an eroded hilltop on this limestone residuum with a lot of clay-rich soils, and that the gullies or small valleys coming up from all sides may well have been changed quite a bit by construction practices. The school we've picked in the Piedmont province, pretty much at random, is Goochland High School. You can see it sitting out here in a broad swath of what's mapped as purple rock, and you go in close, you can see that is a garnet biotite gneiss. Of course, that's metamorphic rock, and all of the rocks in the area are some version of igneous and metamorphic rocks formed during a period of great mountain building. The school itself also sits near the top of a hill. Notice this road intersection kind of for reference site. We plot the stream patterns on here, and you can see also the streams run away from the hilltop, and the hill slopes in the school area are largely pretty radial, going away from the hilltop, although near some of the stream valleys the slopes do go straight down to the river channel. The aerial photo from the school shows the extent of the fields and the woodlots. This is, again, best used as a base map for plotting your locations for where you do field work, and maybe some um, drainage pathways might be visible as you get down on your ground and say, oh, that's what that means when you look at the photo. The wetland map doesn't show any wetlands near the hilltop. If you back up, as I've done here, and you can see the school off to the left, the nearest large wetlands are actually some palustrin forests, wooded swamps, down at the bottom of the hill over near the creek that's off to the east of the school. If some of that land is accessible, that could be a very interesting site to work. But even so, at the top of the hill, we can see some very interesting soils. The very red soil that shows up here on the hilltops is often found across the Piedmont, called the Cecil soil. And the data on that clearly show it's well drained, as that reddish color should indicate. It is not a wetland soil. And this is residual soil weathered from granite and gneiss. Granite and gneiss weathers very nicely, many times to great depth. And so we often get a residual soil that still has the pattern of the rock in it, but a lot of the minerals have been removed. And so it's relatively easy to dig through this stuff with a bulldozer. So it's very common to see big areas of this residual soil, these residual rocks, sculpted into different sort of landscapes so they can put big box stores on top of it. This material is called saprolite, rotted rock. It's very common across the Piedmont. As you dig down through the Cecil soil, again, you see some variations. You've got, going down through the clay, for example, you find maybe 15% at the surface, but it gets almost 50% then at depth. Percent sand does the same sort of change. It's actually pretty high at the surface, but then drops off after about 30 centimeters, going down to pretty low percentage with depth. The change in permeability is pretty dramatic too, although you notice the clay-rich soils at depth here are far more permeable than the clay-rich soils we saw up in the valley and ridge. Here we've got permeability of some 30 millimeters per hour rather than the 3 that we saw up on the clays up on the limestone residual. Again, the question you can ask at a place like this is this information accurate? Do you get the same kind of numbers? And how do these soil properties vary across the area? Also, how does the the water quality change as you go across the area? Do you find runoff from parking lots or from eroded sites that might change the quality of the water going down to the watershed further down? One place where you may see some interesting variation in the soil is off on the north side, up there near one of the ball fields. If you look at depth, you see that the soil is quite gray, with a higher water table at sometimes. This may be an area where there has been a change in topography over time. In the Piedmont, we very commonly see in some of these, even small stream valleys, relatively thick masses of sediment that have washed off of the hill slopes down into the low spots and still haven't been flushed out of the low areas. They will have buried the previous colonial era floodplain, so that you sometimes find dark peaty materials, sometimes even down at depth. We call these legacy sediments, left over from the erosion from farm fields of the last 3 and 4 centuries of farming. Very common features that we find across the Piedmont. It may be that the soils are telling us you're going to see something like that up on the north side of this school. So the general setting for the Goochland County High School is sitting up on top of a hill, on top of a Cecil soil body there, and we've got these rolling landscapes formed in a mixture of gneiss and schist and granite that had now deeply weathered to saprolite. So Goochland High School here is actually quite typical of what you might find in many places across the Piedmont. In the coastal plain, we picked out of the hat the Woodside High School here in Newport News area. You see it's on the broad swath there of the yellow and orange kind of soils. are rock units known as coastal plain terraces. As you get close down look at this particular site, you see that even sort of backing up from the high school, we see very broad expanse of this Chuckatuck formation. If you read carefully there, that says interbedded sand, gravel, silt, and clay, which is very common in these packages of flat sediment that we call coastal plain terraces. Usually it's mud at the surface, there's a sand bed in between, and the gravel down at the bottom can sometimes be pretty thick. Sometimes it's just a trace. But that's what you find typically under one of these coastal plain surfaces. Turns out the Chuckatuck Formation is not the oldest. There are older surfaces that formed when the sea level was even higher, farther to the west, and younger, farther to the east. So we call this sort of a middle-aged quaternary unit. It's going to be moderately weathered. There are going to be some streams that have cut valleys down into this, but you do still have a lot of broad flats, like the one we're seeing here, remaining on this middle-aged surface. Here you can see the topographic map, the very broad expanses of woods there with no very few contour lines indicate just how flat this region is. You can spot wetland symbols scattered across here, indicating there are some wet spots out across this broad flat surface, probably with a mud top. So the problem with coastal plain topography is that if you have these broad flats, it's often pretty tough to figure out which way the water is really going. Most of the topography that we see on the coastal plain has been built by humans. The ramps to the interstates, the abutments for railroads or ditches that we find around that farmers have put in, those largely control where the water goes. So we get some information from this about water flow directions, but perhaps not very much. The aerial photography, again, is going to be very good for a base map. Here you can see where the school is. Actually, let's go, if you go back to the previous diagrams, you'd recognize that where the school is sitting now was not mapped on the original map at all. So this has been a relatively recent addition. When you add in the wetlands in the area and back up just a little bit, you see there are quite a few wetlands off to the east, but they're very sort of spotty, scattered. It's a rather different, unusual pattern for wetlands. In fact, if you back way up and look at the whole wetlands map and combine it with the geology map to make them show up, you can see that there are scattered wetlands across the whole area off to the east. This is actually a quite unusual zone because all of these are sitting in sinkholes. You can also see this pattern in the aerial photography. If you notice all the little irregular black spots, these are actually water bodies or small wetland locations formed in depressions. There is a unit below the Chuckatuck, this big sand sheet. Below it is a shell hash in the Yorktown Formation, a big thick unit of busted up shells, and that zone is dissolving. And as the shell hash dissolves, the sand lying over the top of it collapses down in and forms a depression. This particular area of all of these small lakes and wetlands has been long known as a bird habitat for the migrating waterfowl, and it's been recognized as the Grafton Sinkhole Plain. Well, Woodside School is built right near the edge of that, and you can see one of these wetlands with the soil maps showing up with the Bethera silt loam showing in it. Even looking at just the color through there, you can recognize this is a wetland soil because it is also gray. There are other spots along through here that have slightly higher ground. You see this particular soil body, it's actually a mixture of the Bethera plus the Slagle soil. The Slagle is a good deal more oxidized. So there's a lot of lumpy, bumpy, hummocky ground through here that the high spots have well-drained, better drained soils, and the low spots are depressions. It's a very common thing to find in the coastal plain. Here you can see what colors in some of those kinds of soils would look like. The better drained, moderately well-drained profiles would have that more rusty color to it, and the darker soils without all the rust would be would have formed in more poorly drained situations. So this is what the soils out there might look like. Now, digging down into these, you can get some obvious differences showing up because of the color. So that would be certainly something to note, and that's the immediate clue that perhaps the oxidation reduction differences are there. So in the Bethera, for example, you can see the poorly drained soils, and yes, this is a wetland soil sitting on top of marine deposits. Well, the key question is, how does this difference in drainage affect any of the soil properties? And really the one that it affects most is organic material. Where the soils are wet, close to the surface for a long time, you can actually preserve the organic material that falls from leaves and twigs and roots and all. And that builds up in the soil to darken the soil, as making a higher percentage of organic material. Here you have perhaps as much as 3% organics, which can stain the soil pretty good dark color. Looking at the slagle soil, for example, you see it's moderately well drained, and so accordingly the organic material is much lower. It's about what we've seen in the other soils, between 1 and 2%. So the chief thing you can see with soil drainage differences is the difference in organic material and in color, which kind of go hand in hand. The other thing that you can check in these soils is to look to get a probe out there and check the dissolved oxygen content. This needs to be done in the ground. If you actually pull it out in a bottle and carry it around for a while, of course it mixes oxygen into it and it doesn't work very well. But if you can get a hole, shallow hole with water standing in it, and you can get your probe down into that hole, you probably will find that the oxidized soils, the better drained soils, are going to have a higher oxygen content. This, of course, affects the chemical processes that go on in the soil, and one of the reasons that the wetland soils are so very valuable to cleaning up things in the ecosystem is that there are some processes that sequester certain types of contaminants in reducing conditions, whereas in the oxidized soils it doesn't stay in the soil. So those oxidized and reducing conditions are very important to know about. Of course, the other thing that happens in wetland soils is that the wetness in the soil, saturated water conditions, are not conducive to roots. Roots don't like to grow in always saturated soil, and so you'll see a difference in plant types in the saturated soils versus the non-saturated soils. So what we're seeing then at the Woodside area is that perched up on what might be a slightly higher terrace here at some location with the Bethera soils is a typical sort of flat marine terrace. Because it's so broad and flat, it's typically going to have very poor drainage. Commonly, you're going to see a lot of wetlands scattered across that surface because that flat area simply cannot shed water very efficiently. So what we've tried to talk about are examples at 3 different spots across the state in 3 different geological provinces. These are the biggest provinces in the state, and hopefully the examples that you see here will be things that can carry over to what you're going to find at your particular school. If you happen to be living in the Appalachian Plateau, the Valley and Ridge example is very close to what you may find out in the western part of the state. And for those few schools that are actually up in the Blue Ridge, which is a very narrow province, take a look at what we've talked about with the Piedmont. Good luck with your project.